All right, I'll just start by doing a very quick intro. Welcome, everyone. So nice to see you all. So nice to see some familiar faces and names as well. So just some information. This is a lecture series organized by Science in the News. Science in the News, SITN. You'll see it in a bunch of our names in the Zoom as well. We are a graduate student organization based in Harvard, and our goal is to sort of make science more accessible, share our exciting new scientific work with you all. Our website has lots of blogs. We organize many other things as well, but this lecture series is our baby, and we really enjoy the series. So basically, a few logistics. So this is live on Zoom and on YouTube. So if you're on Zoom, you won't really have the power to unmute yourself, but you can feel free to use the chat in any way you'd like. This time it's pretty special. So if you've come to the previous one, we've had one full lecture in 3 parts. Today it's very exciting. We have 3 separate talks by 3 separate speakers, all in the energy theme on how we can reach climate goals. So after each talk will be 15-ish minutes, and then we'll have questions in the end after each section. You can write your questions anytime in the chat, but we will ask them to our speaker at the end of their presentation. Those are the logistics for Zoom. On YouTube, you can still ask questions on YouTube as well. We will relay your questions on YouTube to our speakers as well, so feel free to do that. If you're on Zoom, you can ask to be unmuted and ask your question verbally as well. So that's an option if you're with us on Zoom. Also, if you have internet connections and Zoom isn't working, you can always flop over to YouTube and do that kind of thing as well. And if you have any technical issues, you can message anyone with Science in the News in their name. So yeah, we're really excited to see you all. Thank you for joining us tonight. I'll introduce our first speaker, who's going to talk about batteries, and then the next talk will be about windmills, and then the last one will be about markets. So that's why we have these 3 separate themes that relate to energy. So yeah, Brooks, it's all yours.
Thanks, Bruce. So hello, everyone. Good evening. Today, I'm going to be talking to you guys about batteries and how that they could make grid storage cheaper and enable more renewable energy. So specifically, I'm going to be talking about sodium-ion batteries. And sodium-ion batteries are a battery technology that's still being researched. And in particular, I'm going to be focusing on some of their scaling challenges. So moving from the lab scale to the manufacturing scale. And let me go ahead and just provide a little bit more context about myself. My name is Brooks Klingman. I'm a MIT graduate student in the Department of Material Science and Engineering, and I'm very excited to be talking with you guys tonight. So without further ado, I'm going to go ahead and get right into it. All right, so renewable energy is on the rise, wind power and solar power, but there is a challenge. The wind doesn't always shine, and the sun doesn't always shine, and the wind doesn't always blow. And on days when it's cloudy and at night and on not windy days, you don't get as much renewable energy. And there are a lot of different proposed solutions for how to get around this problem. But one of those is energy storage, storing energy when it's very plentiful and releasing it when demand is really high. And one of the ways to provide energy storage is with batteries. So I'm going to go ahead and ask you guys a question. So if you're here on Zoom, you'll get a pop-up. And if you're on YouTube, go ahead and just put an answer in the chat. But I'm interested in knowing, what type of batteries do you think electric vehicles use to power their electric motor? And it's multiple choice. And also, if you're not familiar with batteries for electric vehicles, definitely don't worry. This is not a quiz. But I've also got a hint for you guys. The 2019 Nobel Prize in Chemistry was awarded for this battery technology's development. Okay, so while you guys go ahead and ponder this question, I'm going to go ahead and switch gears for just a second, but I'm going to come back to this momentarily, so keep this in mind. So now I want to talk about energy storage for the electric grid, so not electric vehicles. And in the United States, energy storage for the electric grid is dominated by lithium-ion batteries. And right now, there's about 5 gigawatt hours of energy storage, which corresponds to basically the amount of energy it takes to power all of Cambridge, Massachusetts, which is a city that if you were live here with us, you would be in right now, to power Cambridge for 4 days. So this is a lot of energy, but it's about to go up by a lot. In the next 9 years, energy storage in the US is projected to grow by 150 times. So, this is a big time for energy storage, and it's dominated right now by lithium ion. So let's go back to this question that I just asked you, talking about electric vehicles and the batteries that are used for them. And it turns out that electric vehicles also use lithium ion batteries. So this is really interesting because now we have these two different applications that are both relying on the same battery technology. And it's interesting because these two applications are actually pretty different. If you think about it, electric vehicles are inherently mobile. And because of that, the size and the weight of the batteries that go into them are really important. And, over the last several decades, lithium ion batteries have been built up and optimized, basically for applications like handheld electronics and electric vehicles that are really weight and size critical. And in contrast, when you think about the electric grid, it's inherently immobile. It doesn't need to move. And therefore, the weight and the size of the batteries that are used for storing energy for the grid, the weight and size don't matter nearly as much. And instead, it's just the overall cost that's the most important parameter. And so kind of keeping in mind that these applications are rather different, it raises this question of, okay, is there perhaps a better battery for this other application? And the answer is maybe, and that's one of the research questions that we're trying to answer. And in particular, researchers are interested in sodium-based batteries. So sodium-based batteries, if this is the first thing you think of, table salt, you're not far off. Now, salt to a chemist would be more well known as sodium chloride. And if you were to take your microscope and you were to zoom all the way in on a single piece of sodium chloride, you would blow this up and you would see that sodium chloride is just a combination of sodium elements and chlorine elements. And then if you then dissolve this in water, you would be able to get just your sodium ions floating around. And that's what we're talking about. And I kind of threw out a little bit of jargon there, sodium ion. For the purposes of this talk, you can think about a sodium ion as just an element of sodium that's taken on a positive charge. So up till now, I haven't really explained why sodium-based batteries might be exciting. And that's what I'm about to do. There's really three big reasons. The first is that sodium is chemically very similar to lithium. It has a lot of the same properties. And so lithium-based batteries are excellent. So that makes it a great starting point. Now, the main caveat is that sodium is heavier than lithium. And so that's why, so it would therefore have a lower energy density, and it wouldn't be as suitable for an electric vehicle, for instance. The second advantage is that sodium is about 1,000 times more common in the Earth's crust than lithium. And as a result, correlated to that are its lower mining and refining costs that lead researchers to think that the ultimate batteries that we would produce would also be much cheaper. And finally, there's a third main point that I want to highlight, and this one's a little bit more nuanced. But sodium-ion batteries are based on lithium-ion technology, and the big consequence of this is that we don't have to reinvent the wheel. Research is simpler and scale up is simpler. And because of that, that's a big advantage for sodium-ion batteries over, say, something that's much different. So now I want to talk to you guys just a little bit about how a sodium-ion battery works. And I definitely want to highlight that I'm going to kind of throw out a couple terms here, and you don't need to worry about remembering them. It's just to kind of introduce some of the concepts. So there are four parts. There are four main parts to any battery. The first two are the cathode and the anode, and that's where the actual chemical reactions occur that store and release energy. And in between the cathode and anode are an electrolyte and a separator. And the main function of these are to allow the sodium ions to flow between the cathode and anode. Now, the last part of the battery would be an external wire, through which electrons flow. So, yeah, I definitely want to reiterate, don't be scared off by these terms. I just want to kind of introduce some of the main concepts. So I have a little bit of an animation here, and I'm going to go ahead and play it and then explain a little bit about what's going on. So the first thing to notice is that while this battery is charging and discharging, the sodium ions are moving back and forth between the cathode and the anode. And they're flowing through the electrolyte and separator. And then at the same time, electrons are flowing through the external wire. And those moving electrons are generating current. And that current can be used to charge your phone. It can be used to do anything that you do with electricity. And then the only other thing I'd like to say is that, for any battery experts in the audience, you'll know that there's definitely more nuance here. And this is just to kind of talk about the big picture. So this is very similar to the way that lithium-ion batteries operate. And the main change to go to a sodium-ion battery is to the cathode. And that's where a lot of the research is focused right now. They're still working on figuring out what the best cathode materials would be. So I want everyone to just take a deep breath, and don't worry, because this was the most technical, the most complicated slide, and it's all downhill from here. So I have a question for you, another poll. I want to know, have you ever made a pizza? And this one's also multiple choice. So if you're on Zoom, go ahead and put your answer in. And if you're on YouTube, I'd appreciate it if you'd just put something in the chat. And you might be wondering, Brooks, I thought we were talking about batteries. Why are we talking about pizza? And the answer is, it's because that batteries have a lot in common with pizza in a very specific way that I'm going to be talking about. So in that particular way is scaling challenges. So, here is a very small pizza that you could have made from scratch. But if you're like me, then you're pretty hungry, and this small pizza is not going to satisfy you. So one way to have more food to eat is to increase the size of the pizza that you're making. You could scale up the size. And if you did that, you might end up with a pizza like this, which is obviously much bigger than this small pizza. And this sounds great, but there's a little bit of a catch. This comes with scaling challenges. And for any chefs or cooks in the audience, you'll definitely know that the surface area to volume ratio on these two pizzas is very different. And so, you would expect that these cook very differently. In general, the materials properties are different, and you have to take that into account. So if that scares you off, you said, okay, bigger is complicated. Another option is you can make more small pizzas. You can make a lot more small pizzas. And to do that, you would probably need a factory. And at this point, you probably reinvented bagel bites, which is awesome. But this also comes with some challenges. One of those is that to make this many pizzas, at such a high production rate, you're going to need completely different process equipment. You're not using your oven in your home anymore. Now you've got big assembly lines, big conveyor belts, giant ovens, big dough rolling machines. In addition, your process cost is changing a lot too. So you're probably aware of the concept of economies of scale. Your price per pizza is going to change quite a bit. And if you were to do both of these, if you were to scale by size and scale by production rate at the same time, you'd end up with something like your frozen pizza from the freezer aisle in your grocery store. So a big pizza that's also mass produced. And as a small caveat, in preparation to give this talk, I learned actually quite a bit about how frozen pizza is made, and I'd encourage you to look up some YouTube videos because it's very interesting. Okay, so Brooks, why are you telling me about this? This is still all about pizza. And the answer is that batteries have all of these same challenges. And particularly right now in the lab, people are making small batteries at a very small production rate. And in order to have an impact, those batteries need to both get larger in size and increase in production rate. And when they do that, they're going to have these exact same challenges. So let's kind of take a look at what that looks like visually. So here's an example of probably a researcher who's working on making batteries at the lab scale, and they're working with small quantities. Everything that they're doing is very manual. The oven that they're using is probably rather small. The actual battery they're producing is probably rather small. Probably just a little coin cell that you might see in your watch battery, like a battery that would go in your watch, and the actual quantity of batteries they're making is going to be really small. And this is how it's done in the lab. Now, in contrast, if you scale this up, it looks completely different. And so this is a video that I pulled off of Tesla's website. This is from their lithium-ion battery manufacturing plant. So keep in mind, this is a lithium-ion battery. Sodium-ion batteries, which is what I'm talking about, haven't been scaled up yet. That's what we're researching. But the manufacturing process is going to be very similar, or we expect it to be. And so this gives you a little bit of an idea of how different it is, and how there are inherently scaling challenges to go from this small picture up in the top right corner to this video that I'm playing right here for you now. And again, the point of this video is not to understand all the individual details that we're seeing here. Instead, the emphasis is just on how different and how fundamentally different it is to produce batteries at a manufacturing scale. So one of the kind of the most obvious kind of consequences that comes out of looking at something like this is clearly the cost structure has got to be different when you make batteries at a manufacturing scale. And it is, but can we predict that? Because that's really important, because we're trying to make these cheap batteries for the grid. Can we predict how cheap they're going to be? And the answer is yes. And that's again what I research. And the way that we work on this is, we take our battery recipe and we break it down into its component steps. And if it's starting off as a laboratory recipe, then we think about what those steps look like at a manufacturing scale. And then for each of those operations, we think about the different costs. What are the raw materials costs going to be? What are the equipment costs? What are the labor costs? And it's at a high level, it's a pretty simple concept. In kind of as with many things, the devil is in the details, and the art here is really getting really good data and building the model in such a way to get an accurate result. And when you get these results, what they can tell you and what they can allow you to do is anticipate where some of the manufacturing challenges are going to be, and pinpoint, for instance, where the biggest costs are and where a lot of the attention should be. So I'm kind of starting to wrap up here, and you might be wondering, okay, this is all very interesting, but what's the point? Why do we care so much about this? And the reason is because to scale up materials-based technologies, it takes a really long time. And here are two examples: one, photovoltaics or solar panels, and another, lithium-ion batteries, which is very pertinent. It takes about 30 years to go from basically, proof of concept in the lab to mass production. And 30 years is a really long time to get a grid storage battery that's cheaper than what we have currently. And if we can anticipate some of these manufacturing challenges and speed this up, then that's really going to help us out. And thinking about this a little bit more, if you really want to summarize my talk in a single expression, it would be accelerate by anticipating. if we can anticipate where these red rectangles are in the scale up process, where we're going to waste time and money, and we can cut those out so we can scale up faster, then we're going to benefit. So let me go ahead and recap what we talked about a little bit here today. So we started off by talking about how batteries for the grid are inherently a different application than electric vehicles. In that application, the weight and size are much less important. And that kind of leads into this idea of, hey, maybe sodium-based batteries could be cheaper and more suitable for this application. But scaling those batteries up is going to have a lot of challenges, and trying to understand those is going to help us to commercialize and accelerate this technology faster. And that's what my research is all about. And ultimately, if we can enable grid storage, to be cheaper, we can lead to more renewables. So I'm happy to take your questions now, if you have any questions. And that's all I've got to say.
Thank you so much, Brooks. That was fascinating. We already have one question, so let's start with that. It's from Eric, who's on Zoom. What's happening with flow batteries? I remember hearing about the Rhubarb battery about 5 or 6 years ago.
Great. That's actually, that's a really interesting question. So for those of you who don't know, a couple of years ago, there was a press release that came out about there was a lab at Harvard that was working on basically batteries that used a similar material that's found in rhubarb. They're using that material to make batteries. And what was kind of interesting that came out of that was, or at least my conclusion was, that rhubarb-based batteries are not the future. You can make batteries out of a lot of things. The question is, ultimately, how costly is it going to be? What materials are it actually being made out of? Are they sustainable? Do we have access to them? But so I don't study flow batteries, so I can't tell you too much about the precise development there. I can tell you that some of the advantages that flow batteries do have is that they can decouple. They can decouple one of the biggest trade-offs in like a standard lithium-ion battery, which is between energy density and power density. With regards to flow batteries, you can get away from that limitation, and that's pretty exciting. I know a lot of people are really excited about that. So that's definitely not a direct answer to your question, and I wish I could elaborate a little bit more on flow batteries, but hopefully I get to that point in my research in the future.
Awesome. Thank you for that. Eric, let us know if you have follow-up questions, but I'll move on to the next one. It's from Ryan, also from Zoom. What are the pros and cons to scaling up by making larger sodium-ion batteries versus making more small sodium-ion batteries?
Right. So, we have to do both. Right now, the batteries that are being made at the lab scale are a typical battery you would see made at a lab scale is a little coin cell, like you would put like in your watch, and that's not that's not like the right form factor for for something like an electric vehicle or for the grid. But that being said, the solution is not to make a battery the size of your house, because at that point you could have a lot of thermal management challenges. So in my mind, probably ramping up the actual mass production scale is more important than the size of the battery. If you were going to make like millions and millions of these coin cell batteries, that would be more advantageous than making one house-sized battery. So hopefully that starts to answer your question. And are we getting a question coming through written down?
Yeah, we have a handwritten question. Thank you for answering Ryan's question. And
Okay.
now I think that's Neil's question. How do you dispose sodium batteries? Thanks. Oh, Nell, sorry. That was
okay.
Yeah. Thanks, Nell.
Right. Okay. So good question. So so right now, like, sodium ion batteries aren't being mass produced. So kind of like their end of life is still kind of an open research question. And in kind of, it's an interesting topic because, for instance, lithium ion batteries, now that they are being mass produced, especially for electric vehicles, that application is really taking off. There are a lot of questions about how to recycle them. And it turns out to be kind of challenging. And the interesting potential for sodium ion batteries is because the design is still so in flux. There's an opportunity to select materials and to select designs that are amenable to recycling or and disposal, which basically, there's so many advantages to that. One of them being that you can get this circular economy concept where you can reduce your reliance on foreign imports. You can create a domestic value chain where you're generating growth, economic value domestically. There's also the sustainability lens where you're doing less, mining, in other locations. So yeah, right now, sodium ion batteries aren't really being disposed on any mass scale because they don't exist. So that's my spiel.
Awesome. We have another follow-up question. Could mass-produced small sodium-ion batteries be used in electric vehicles?
Right. Okay. So the short answer is probably no. And the answer is, and the reason why is because of one of the points that I made a little earlier on, and I made it so fast. There were a lot of points that it's definitely easy for things to slip through the cracks. Sodium ion batteries are going to be less energy dense than lithium ion batteries, and so basically the batteries are going to be bigger and heavier, and because of that, sticking them in electric vehicles is going to reduce their gas mileage. It's going to reduce their range. It's going to increase their cost. It doesn't make sense to replace lithium ion batteries with sodium ion batteries for electric vehicles. But for the grid, where you don't have to worry about the weight and size, and just the overall cost is what's most important, that's where something like this could be exciting. So I guess I want to do a quick time check. We've got 2 more exciting presentations to get to. How are we doing on time?
If we have no more questions, let's wait for a few seconds and let's check. I think we're good. Then we can take a break and then we'll be back with our second talk. Thank you so much, Brooks. This was fascinating. Very cool work. So bio break. We'll be back here at 7:05. So we're taking a 5-minute break to come back to our second talk of the night. Welcome back, everybody. Hopefully you're slowly walking back to your computer. A few logistical things. So we do have 3 separate speakers, but if you suddenly have a revelation about batteries and want to ask it to Brooks, you can still put it in the chat and we can ask it at the very end to all 3 of our separate speakers. So just a quick note, don't worry, Brooks isn't gone forever, he's here. So we have our second speaker now. And one thing I forgot to mention at the very beginning is all 3 of our speakers today are from an MIT course that happened over winter break that was about science communication. So I see Diana in our audience. Thank you for making this collaboration happen. We're really excited to collaborate with this course at MIT. Yeah, so this is the second part. Again, feel free to ask questions in the chat throughout and we'll get to it in the end. And now Ming Hao will talk about renewables. All yours, Ming Hao.
Awesome, thanks. Welcome back, everyone. So this is the second part of our how to get climate tools theories. And in this part, I'm going to talk about wind power and air quality. Brooks have gave a fascinating presentation on sodium ion battery, and he ends on a perfect spot for me to start my presentation, which is how the battery technology can enable us to have more and more renewables in the future. And my talk will be on a specific set of benefits or impacts of renewable energy on our life is on air quality and human health. So again, my name is Minhao Chu. I'm a PhD student at MIT. My research is on environmental science and policies with a focus on air pollution, climate change, and energy issues. So we talked about renewable energy a little bit in the last talk, but let me take one step back to think more broadly about climate policies. And of course, renewable energy development is sort of the centerpiece of that. So you may have heard of two myths around climate policies from different kind of channels or sources. So the myth number one is you may have heard some other people saying that benefits of the climate policies are really far in the future. It could only be observed 50 to 100 years or so. It's really about the next generation. It's not about us. A second myth, sort of similar, is that the climate policies only help communities near coast, or if they live in tropics, or if they live in those climate sensitive regions as we consider they are. So in this talk, I will like to actually try to explore these myths, and in the end, we'll come back to that, whether these two myths are true or false. Answer alert, those are falses, but I'll briefly explore one specific perspective on this, is that through the lens of how do climate policies can influence air quality. So let's stay for those two myths for a second and to discuss why they may sound correct or why at least they are partially correct. And that has to do with the lifetime of different pollutants we emit when we burn fossil fuels like coal or natural gas. So here's a figure of a coal power plant. So we know that the coal power plant, it burns the coal to generate electricity. It emits carbon dioxide, CO2, which is the leading greenhouse gases that can warm our planet and change the climate. One thing that is sort of justified the two myths are that the carbon dioxide is not a very reactive species, right? So it cannot react with a lot of things in the atmosphere. So it tends to stay in the atmosphere for very long times, usually longer than 100 years. So that is to say, even we take action now, the CO2 we already emitted will be there for a long time, and that is why sort of the myth number one said that the climate benefits will be far in the future. But another important set of things emitted from coal power plants or fossil fuel in general is what we're going to talk today is what we call criterion air pollutants. So what I mean by criterion air pollutant is these air pollutants are currently under regulation in the United States, right? So there are currently 6 types of air pollutants under regulation in the United States. There are certain limits on that. If it's above that limit, then we said this is unhealthy to the human health, to the human health. And there are also other kind of regulations on, say, coal power plants on how much of those pollutants they can emit. For this type of pollutants, their lifetime is very different. So they only last for a week, right? So those pollutants, they will be washed out by rain, they will be blown away by wind, et cetera, So the idea is that if we can remove all those criterion air pollutants today, basically in a week time, we will entirely get rid of that. And then we'll come back to this timing point because that is important for falsifying the myth number one we have. So let me be a little more specific about the pollution we're talking about today. So among the 6 regulated pollutants, one of them is particularly important, and that is particulate matters, or PM 2.5 in this case. So PM 2.5 are these small particles that suspended in the air with diameter less than 2.5 microns, which is really small. So here is a figure showing comparing to PM 2.5, which is the small dot, with another type of particulate matter, which is slightly bigger, PM 10, compared to human hair. So this is really saying this is tiny particles that we cannot see in the real world. but it has a devastating consequence on human health, and there is a lot of evidence on that. So because these particles are so small, so they can actually get deep into our respiratory system, right? So what this figure is showing that is those large particles, if the particle has a diameter larger than 10 microns, then it will be blocked by our sort of first layer or the upper respiratory system. But because the PM 2.5 is so small, so it can actually dodge away from our blocking system and really get deep into our lungs and respiratory system and causing a lot of health problems. So now let's come back to the original theme we have, which is renewable energy and air pollution. And in particular, I'm going to talk about wind power and air pollution. So the reason, so Brooks mentioned this a little bit, but the reason we talk about wind power is because it is now becoming increasingly important in the electricity grid in the US, but also really all over the world. Right, so here is a figure showing that among the electricity we added in the year 2020, about 44% of them is wind power, and really the other 32% is another renewable energy, the solar power. And what I talk today, although it will be mostly focused on wind power, but a lot of things also apply to solar power as well. So why does wind power can help reduce air pollution? So let's compare wind power with another two popular sources of generating electricity, burning coal or burning natural gas. And I'm going to show you their emissions in two chemicals. Those are sulfur dioxide, SO2, or nitrogen oxide, NOx. So these two pollutants will, in the atmosphere, reacted to become the particulate matters that we talked before, right? So most PM 2.5 in the atmosphere is not directly emitted by power plants or other sources, but is actually a reaction between different chemicals. And the most important sources of PM 2.5 are these two chemicals. So what we know is wind power has a little bit environmental footprint, you can say that, right? It does have a little emissions. It has this little emissions because even though when we generate electricity with wind power, it does not produce any pollutants at all because we don't burn anything. We just let the wind power do its trick. But when we build those turbines, we rely on things like cement or iron steel, and producing them usually has some emissions. But overall, this is the emissions of the building a wind turbine. While every kilowatt hour of wind power emits this amount of SO2 and NOx. On the other hand, coal and natural gas have a lot more emissions and therefore air quality impacts. Right, so coal is in particular dirty. It's about 60 times SO2 emissions of the wind, or 20 times the NOx emissions. Natural gas is slightly better, but is still overall much worse than wind. So with that, so in theory, wind should help us reduce pollution because it will displace the other two much dirtier sources. And let's talk a little more about this replacement. And this replacement in many parts of the country in the US is operated or is due by this electricity market. So what the electricity market is about is it will decide which power plants gonna to generate electricity. And this is, you can think about this as some kind of an auction process. So this electricity market usually includes several states. They will say, well, for the next hour, we are going to generate this amount of electricity to meet our consumers' demand. Who are willing to generate those? So all the power plants are willing to generate those because that's how they make their money. And what they do is they will make a bid to say, I can generate this amount of electricity with this amount of prices. And the auction is carried out in the way that whoever can generate the electricity with the lowest cost will win the bid and can generate, because the market is usually very large. So one power plant cannot meet the demand. So we'll move on to the second one with the second lowest cost, so on and so forth until the supply meet the demand. And in this market, there will be different kind of power plants: wind power, nuclear, coal-fired power plants, natural gas, etc. And this, as I said, this market is determined based on the generating cost. And let's take a look at the generating cost of this, again, the three dominating sources of the electricity generation. So wind power has close to zero cost to generate electricity. And to be more specific, what I'm talking about here is this variable cost, right? This is to say, once we already have the turbine there, or once we already have the power plant there, how much cost do we need, or how much cost does the plant need to generate one extra unit of electricity? And wind power doesn't need too much cost because you just let the wind flow, you just let the wind blow the turbine. So it's close to zero. And on the other hand, for coal or natural gas, there is some cost because you have to burn that amount of coal or natural gas to actually generate that electricity. So as I described earlier, the market will first let those units that can generate electricity with the lower cost to generate. So wind power can always generate. So that is why when we have more and more wind power, the wind power can always generate, and it will displace the other more expensive fossil fuel sources. So that's why wind power, when we build more wind power, we can improve our air quality. So what's important here is that it's not about some policy priority that the government wants wind power to be there. It's really sort of the economics that because wind power has really very little cost. So as long as we build more wind power, we let them generate, and that can improve air quality. Okay, so far in the theory, we have established that if we build more wind power, we should be able to see air quality improving and air pollution reducing. And my research is really, is this really the case? Or can we actually see that in the real world data? So here's a map of all the wind power turbines in the US in the year 2016. And our question is, does those fossil fuel power plants actually emit less air pollutants when we build more wind turbines? And this question is made possible in the US because in the US we have really good data sources that the EPA did a pretty good job in documenting the emissions of all the fossil fuel power plants. But on the other hand, this is a very tough question because a lot of things are going on and it is hard to establish this causal relationship. So there are two ways that we can sort of detect the impacts of wind power on air pollution. So one way we can do that is we can compare, let's say, the emissions of power plants in the year 2021 compared to the emissions in the 2001. And the idea of this comparison is in 2001, we have very little wind turbines, and in 2021, we have a lot of wind turbines. Unfortunately, and you may already have the sense that this comparison doesn't really work because in the 20 years time, too many things changed. And to just name one perspective of that, this is the cell phones that people use in 2001. And I'm just a first year primary student in China, and I'm not sure I have got a cell phone like that time. And this is the cell phones we use right now. So really too many things change in 20 years, and specifically related to this topic, the environmental regulation changed, the generating technology changed. We cannot just establish this causal relationship. Alternatively, and this is the strategy we actually used in our research, is to compare this on an hourly basis in a much shorter time period. So let's say this is actually the weather in about a week before in Boston. So at 9 p.m. in February 15th, the wind speed is about 14 kilometers per hour. But really, just in an hour, the wind speed changes, increased by about 50%. And I'm sure the audience has some kind of personal experience that the wind can really change very quickly in a very short time. So what we are going to do is we'll compare the fossil fuel power plants emissions in this hour compared to its emission in this hour. And this is a plausible strategy because really not much can change within an hour. And we can have with some confidence to say that the emissions differences between these 2 hours, say for a coal power plant in Boston or for a natural gas power plant in Boston, is because the wind power changes and the wind power production also changes. So here is what we find in the results. So in the literature on this, sort of as some of the environmental scientists like me, what people like to do is we want to place a value on those air quality benefits. So I'm actually going to show you the results in dollar terms. So we're going to calculate, first of all, how much does the wind power improve the air quality, and how much this improved air quality can translate into avoided deaths due to, say, respiratory diseases or lung cancer. And then this is common practice, but also pretty controversial, that a lot of regulation body like EPA like to place a dollar value on human lives. So we're going to just follow that, and we'll monetize this. So what we find is the impacts of wind power are pretty large, but also regionally very different. So for instance, in California, this benefits is there, but it's not too big comparing to the electricity bill that Californians pay. This is about 0.05 cents per kilowatt hour comparing to a 15 cents per kilowatt hour. On the other hand, in places like Pennsylvania or Ohio, this impact can be much bigger. So this is about 5 cents per kilowatt hour comparing to the 7 cents per kilowatt hour you pay for a bill. And this regional difference is because in California, the electricity grid is already relatively clean, while in Pennsylvania, Ohio regions, there are still many coal power plants there. So when we have actual wind power going on, it displaces those really dirty sources and it generates a lot of benefits. So let me conclude by saying, although we sort of established that the wind power has some pretty big cost in terms of reducing air pollution and improve human health, it can do better. And it can do better because the market structure is set up to say, as we talked before, is purely determined by the economic cost. And in most places in the country, natural gas is slightly more expensive. So the wind power will actually displace those units comparing to coal units because they are slightly more expensive than coal units. However, as we mentioned as well, coal is much dirtier than natural gas. So if we consider the environmental costs, we should actually prioritize wind power displacing those coal units instead of the natural gas units. So we can indeed do better by designing our electricity market in a slightly different way to maximize the environmental benefits of wind power. So finally, let's come back to the two myths we were talking before. So hopefully I have convinced you that because of wind power or renewable energy in general can improve air quality and save human lives, these two myths are not correct. The myth number one is because the air pollution really lifetime is only a week. So we take some actions, we can see that benefit in a week. So benefits of climate policy are near term. And also it's not really just about the communities near coast or in the tropics. If the community is historically burdened by air pollution near coal or natural gas power plants, then climate policies can also help those communities as well. The last mark I would say is just as we talked in the last slide, the current electricity market can also do better by considering environmental costs. With that, I'd like to take any questions and thank you so much for your time and attention.
Thank you so much, Michal. That was fascinating. Let's get some questions. Please write them in the chat if you have any questions, both in the Zoom chat or the YouTube chat, wherever you're listening to us from.
I have a question. Have you asked the same kind of question about other renewable energy sources? So specifically, like what's the cost comparison to solar?
Right, that's a great question. So we haven't, we didn't do that analysis in my work. Those things will generally be pretty similar in terms of how they sort of work in the electricity market. I think the big difference is that where we deploy solar will be very different from where we deploy wind power, right? So there's a map I showed earlier that there is basically no wind turbines in the southeast US because the wind speed has not been very big, so it's not economically very feasible to build wind power there. But on the other hand, solar potential has been huge for those regions. So I think one big difference is when we compare wind power to other renewable energy such as solar, will be that where they are, and because they are in different locations, so the underlying fossil fuel energy structures will be also different, and that's where the biggest difference comes from.
I actually have a follow-up question on, so because it seems like, so for the wind energy, it depends where you're at, right? With solar panels,
Right.
Well, so how much is the carrying of energy kind of have an impact? So for example, if I'm in a place where I won't have wind energy or I can't have solar panels, is it better to just build a coal plant or to carry something from far, far away? Which one is more environmentally friendly?
Yeah, that's a great question. So, so generally speaking, I think, so when I sort of talk about this electricity market, so they're generally very big. So they're multi-states markets. So, and how those markets work is essentially, it doesn't matter where you build a wind turbine in this market. So as long as you build one, there are minor differences, but they will sort of do the trick. But still, we have this large regions that it might be not feasible to build wind power or solar. And I think purely from an environmental perspective, it will be environmental friendly to import electricity generated with renewable sources from other regions. That might be that might be more or less economically costly. And then we need to do the math of how much you actually gain from the air quality improvements comparing to the extra cost you have to import the electricity from neighboring regions.
Awesome, thank you for that answer. We have some more questions, so I'll read them out. These ones are from Brooks. One of them is, I thought natural gas was cheaper than coal in much of the United States. Is that not the case?
Right. So I think that's a good question. So yes. So especially because of the fracking technology that we do see a lot more natural gas is being built. What I have sort of talked in the presentation is about their marginal cost or their variable cost. So how much cost you need to pay to generate one extra unit of that. And in certain places, it seems like the natural gas is slightly more expensive than coal.
Awesome. There's a thank you about that. And then the other one is, do you know about the potential for wind power along the Gulf Coast offshore?
Right. So that's a great question. So so I sort of talk a little bit in sort of when I answered the other question. So I said the Southeast doesn't have too much potential for wind power. And I only say that because I'm not considering the offshore wind. So if indeed sort of the onshore, especially along the Gulf region, there seems to be some wind power potential there. I think the thing is that the offshore wind power technology is less matured compared to the onshore technology, and there is still a lot more potential that we can actually exploit for the onshore wind in the US. So I think that's why people are sort of prioritizing the onshore wind a little bit more, but certainly there are a lot of potential in the offshore as well. And that can, again, sort of be tied into this air pollution story as well.
Awesome, thank you so much. There's another question from Yulia. I wanted to better understand how the impact was measured based per hour. Does wind generated electricity have to be used right away? Or why was the wind power was used as a proxy? Right,
that is a great question. So that is more related to sort of how the electricity market works. So to answer the question, yes. So basically, the power generated in this hour will be consumed, right? It's like sometimes the electricity gets wasted in certain cases, but that often doesn't happen because there are sort of two separate market systems going on. So one we call day ahead market. So there is this auction prices that will different power plants get to compete for generating for tomorrow. But and that is based on how we predict tomorrow's wind power, sunshine, things like that. But then after for the next hour, things may change, and then just the hour before everything really happened, then there will be a separate market process. So if the prediction is a little off, then this market will also will happen and adjust accordingly. So generally speaking, on an hourly change basis, so if there is a wind changes, the wind power plant will respond to that, and then the fossil fuel products will also respond accordingly, and that has some air quality implications. That is a great question.
Thank you so much. Do we have any other questions? If not, it's actually a pretty good time to take our break. But any last takers? Seems like no. Well, Minghao, thank you so much for this talk. Everybody, thank you for your questions. If during the break you have some questions too, feel free to write them in the chat and we can get to them when we get back. But now we'll take another 5-minute break. Let's be back at 7:42 for our third and final talk of the evening.
Awesome, thanks everyone.
Yeah, sure, thanks. Okay, so thanks Brooks for talking about innovative battery technology to store excess energy, and Minghao talking about some renewable energy. So I'm going to talk about how to reduce energy waste, specifically in transportation field. And a little bit background about me. So I'm Siyu Chen. I'm currently a PhD candidate in Civil and Environmental Engineering department at MIT. So let's begin. Okay, so as you may be wondering, what with the most energy in transportation field, that's congestion. And let me give you some ideas of the congestion measures in on the national level. So as you can see here, I give you 3 measures. The first is fuel wasted in terms of the billion gallons. And the second is delay per commuter. And the last is the total cost, which considering the combined effect of the fuel wasted and the delay wasted. And on the first row, it's the absolute magnitude measure in year 2017. So that's the latest data I can find. And the second row is the 5-year change as a percentage. So as we can see that in year 2017, there are 3.3 billion gallons fuel wasted. And that's a very large amount. And it can fill almost 60 billion bathtubs. So that's a lot of bathtubs it can fill. Although the percentage is 3% increase, it's very small, but considering the base number is very large, so it's still a considerable amount increase. And the second measure is delay per commuter. It's almost 54 hours per commuter, and it is still increasing at a rate of 15%. So that's I think fairly good increase rate. And considering the total cost in terms of the billion of the dollars, it's equivalent to 179, and it's still increasing at a rate of 19%. So that's some background on the national level. What about our city, Boston? Do you think Boston has a congestion problem? I think probably you do. But do you have an idea like how serious it is? Let me tell you. To some of you, it may be surprising, and to some of you, it may not. But the Boston is ranked as the most congested city in America. And the annual delay per commuter is about 164 hours. The equivalent economic loss per commuter is around 2,291. So that's a large amount, dollar amount for each individual. So in the rest of the presentation, we are going to talk about some ways that can alleviate congestion through a very concrete example. So let's think about one day you go to school by car and you realize that it takes much longer time and there are a lot of more traffic on the road than if you go to school in the afternoon on the same road. If you realize this situation, you are experiencing congestion. And the formal definition of congestion is that there's the excess of vehicles resulting the speeds that are slow or much slower than normal speeds. And when you are stuck in the traffic, I'm sure you will have this idea. Why can't they just add another line? And it may be, and you may think like, as the following flow animation shows that once we have a third line, the traffic will move smoother and the speed will increase, but that's not usually the case. Oops. Okay, let me try to go back. Okay, that's not usually the case because first, it is sometimes very expensive and impossible to add another line. Just think about the Boston. Is it possible to have another big dig project in the downtown Boston to increase the capacity of the I-93? I think it's probably not. So that's usually the main reason. And the second reason is that it will cause another phenomenon called induced travel demand. So this means that once the travel or the traffic situation gets improved by increasing capacity, it will boost population growth and attract a lot of people using the increased capacity road. And then as a result, the improved route will eventually become congested again, and you will be back at where you start. So that's why the increasing capacity usually fails. So let's take another angle and think about the congestion problem. Can we try to discourage people traveling and reducing travel demand? And naturally, we can come up with a solution named as the road pricing. What's pricing? The main idea of road pricing is that it will charge travelers if they want to use the road. And the amount of the money drivers have to pay will increase as the roads get busy. And as a result, as the economist has found that road pricing can indeed increase the situation and increase the net social benefit. But however, the problem is that the public will perceive road pricing as unfair or just another tax. And the equity debate plays a very important role that limits the application of the road pricing around the world. And actually, there are no city across the United States has implemented such road pricing. One exception is New York City, which is seriously considering implement a road pricing scheme in the Lower Manhattan area as shown in the following plot. The orange zone is the congestion pricing zone, and all the traffic who enter this zone during the morning peak hour will be charged a toll equal to $10 or $15. And because of the short advantage of the shortcomings of the congestion pricing that drivers have to pay, is there any other solutions that can achieve the same performance as the congestion pricing but does not require additional payment? Indeed, we can consider about the solution, which is a quantity control. And it has a successful applications in other areas. One example is a cap and trade. I'm sure some of you may be familiar with this idea, but I will just do a quick review of it. So the main idea of cap and trade is to reduce greenhouse gas emission. And the government will be responsible to set the total acceptable emissions. And the corresponding credits will distribute to all the factories. And factories have to consume credits in order to produce emission. As shown in the left-hand side graph, the factory one on the left-hand side produced less emission. so it will have the actual credits. And the factory 2 on the right-hand side produce a lot of emissions and need additional credits if the factory 2 want to continue production. So that's why the factory 1 can sell actual credits to factory 2 in exchange for money. And as such way, the total accepted emission will be controlled by the regulator, but each factory can produce the amount that by buying additional credits. And that's the main idea of the cap and trade. To apply this similar idea in transportation field, we can have a name as the tradable mobility credits. And it's simple that the credits used to emit greenhouse gas will be replaced by the mobility credits that's used for traveling. And the factories will be replaced by each individual travelers. And the government will be responsible to distribute all the mobility credits to travelers, and travelers will consume different credits to travel, which are changing by the road conditions and the travel alternatives. In order to operationalize the tradable mobility credit scheme, I'm developing a framework which is named as a Trinity, as the flowchart shown on the left-hand side. It consists of 3 components. The first component is a smartphone app, which is for each user prior to a trip. They can open the smartphone app and have access to different travel alternatives and information associated with travel alternative, including travel time, number of credits needed to pay, and also similar to the Google Map. And also, travelers can use this smartphone app to access their mobility credits account and trade their mobility credits. The second component is the market model, which will be responsible for all the trading behavior. And the market price of the credits will be adjusted according to the number of people, the demand of the credits and the supply of the credits. The last module is optimization module, which consists of 2 parts. The lower part is the user level optimization, which is responsible for providing very good personalized travel menu to each individual through smartphone. And the upper level, which is system level optimization, is responsible for deciding the amount of the credits associated with each travel alternative. And the main highlight of this tradable mobility credits idea is that credits can be traded in the market. Some users can sell unused credits to those who do not have enough credits for their trip at a price determined by the supply and demand. In other words, those who wish to travel at busier time can pay extra, while users are very flexible, can sell extra credits to earn money. And that's all the conceptualize of the tradable mobility credits. How can we really verify that tradable mobility credit the tradable mobility credits performance? We can achieve that through simulations. So the simulation means that we will use a programming language to code different models into a single programming script and to try to mimic the real world. And the different models, including such as the behavior models to model people travel behavior, and the road network model try to model this like real road network, and also the interaction between road network and people's travel. And all those models will be calibrated by the real world data. So we can think like the simulation as a real good representation of the real world. And the benefit of using simulation is that we do not need to pay a very high cost to try to do the real world experiments. And from the simulation, we found that Trinity can actually achieve the same performance as a congestion pricing, and the number of credits charged should increase as roads get busier. And in addition to that, we found that Trinity can attain revenue neutral. This is because, as shown in the following plot, in the congestion pricing, we can see that people have to pay extra amount of money in order to travel, and those revenues will be collected by the regulator. So that's a money transfer from the user to regulator. And for the Trinity, because each user have only to use credits that is distributed by the regulator, so they do not pay the money to the regulator directly. Instead, they will exchange monies for regulators among the users. So that's why there's no money transfer from users to regulator, and Trinity attains revenue neutral. And also, Trinity has the potential to have a higher user equity. This is because for the different groups of the users, for example, for the low-income users, we can just give them more credits, and they can sell those credits for benefit and for the money if they need. So that's why Trinity has the potential to do that. To summarize, the Trinity has the potential to reduce emissions and car accidents and travel delays because as a result of the congestion reductions. And in this talk, we show the three main ideas. The first is that increasing road capacity usually fails because of the high cost and sometimes infeasible. And road pricing, although it's effective, but perceived unfair to the general public. And last, we found that there's a promising method, which is tradable mobility credits, can achieve the same performance as road pricing and attains revenue neutral, and also has the potential to increase user equity. And that's it. Thank you very much. I would like to ask any questions.
Thank you so much for this talk, Sue. It was fascinating. Now I have so much to think about when I'm stuck in Boston traffic.
Yeah.
All right. Type your questions in the chat, both through YouTube or Zoom, wherever you are, and we can ask them to our speaker.
One question. Do you imagine these credits to be specific to like specific roads? If I use more than one highway to get to work in the morning, do I need to get different types of credits?
Yes, so I think the idea is that the credits will be universal, but the amount of the credits needed to use the different roads will be different based on the condition of those roads. And yeah, so if like roads, if for the highway like easily will be congested, then the amount of the credits required will be higher than the free flow highway. And also it can be dependent on the time. Like in the peak hour, it can be charging credits, but in the off peak, there can be no credit charge at all.
Awesome. Thank you for that answer, Sue. We have some more questions. One is, would credits come from local governments? Where would they come from?
Yes, so yeah, so that's a really good question. So currently, I have not think about this question carefully because this research is still like a very futuristic idea, and this question is regards of the actual implementation and operation of this idea. So so there are a lot more need to do research on this, but I think it's for the local, one thing I can think of right now is that for the local government, if they want to distribute those credits, then it will be hard to coordinate among the other cities because some of highways are shared by the cities, and actually some interstate highways are not belong to one city. So that's some questions you need to think about in for this one.
Yeah, lots going on. Another question, how should the government allocate the credits? Is there an optimal way to do that?
Yes, so that's also a really good question, and I'm actually intend to do some more research on this credits allocation in the future. But currently, in the simulation results I have studied, I assume that the government will distribute the same amount of credits to all the eligible travelers.
That makes sense. Now the comment plus question from Brooks. Thought-provoking. You mentioned that congestion pricing hasn't really taken off in the US. Are there certain regions and cities where something like this might gain traction?
Yes, I know some Asian cities and European cities have implemented that. I think Singapore is one example, and actually Singapore has implemented congestion pricing, I think almost 20 or 30 years. It's a very long history. And also I think London has implemented congestion pricing.
Awesome, thank you. We have many questions, so I'll move on to the next. This one's from Ryan. How would you address the risk of political opposition to traffic credits?
Yes, so I would imagine that, yeah, the trade mobility credits will have a lot of political issues similar to congestion pricing, but there's a very, I think, apparent attracting point of the trade mobility credit than congestion pricing is that that's a it's revenue neutral. So I think that point can be very easily accepted by the general public. So I would imagine that it will face a less political challenge than congestion pricing, but I'm sure it will also face a lot. Yeah.
That makes a lot of sense. Another question, which I was also curious about, where does the name Trinity come from?
Yes, so the Trinity, I think it's mainly come from the three components there, and and also it's named by my advisor, and I think he feels religious that day.
Awesome. I think we covered all of the questions. You still have a few minutes to write any questions, but I also wanted to post a link in the chat, which is our feedback form. This could be topics you're interested in hearing about in the future. How did tonight go? Anything we can do to make this sort of seminar experience better for you, please leave your feedback in the form.
And I also wanted to jump in and particularly say if you're interested in another talk about climate change and its impact on human health and related policies, that's actually going to be thematically similar to our talk next week at the same time. So definitely come back.